Today, I wanted to make a quick video about what I call row stuff and column stuff. We're going to start with an M by N matrix, that is M rows and N columns. Let's note that A is a matrix, not an augmented matrix. A is a matrix. The columns of A form a set of vectors in Rm. Each of the columns has an M rows, so that means each column of A is a vector in Rm. So if A is 2 by 3, then we have 3 vectors in R2. If A is 5 by 4, then I have 4 vectors in R5. The main thing that we want to look at when we're looking at a matrix is where the pivots are. And we want to look at what pivots in each row or pivots in each column tells us about things that are associated with this matrix. In particular, we're talking about the matrix A. That's the thing that will have the pivots. It's the matrix that has the pivots. We could talk about a set of vectors associated with the matrix, usually in the form of the columns of A. I could talk about a matrix equation that's associated with the matrix, the equation AX equals B. And I can talk about the linear transformation defined by multiplication by this matrix. The linear transformation where T of X is A times X. So looking at where the pivots are in the matrix will tell us something about each of these items, the columns of A, the equation AX equals B, and the linear transformation T of X equals A times X. So let's look at what we can conclude if we observe that A has a pivot in each row. If A has a pivot in each row, then we'll say that the columns of A span Rm. We wouldn't want to say A spans Rm. That's not how it works. We need to look at, when we're looking at a set of vectors that spans a space, we need to talk about a set of vectors. The set of vectors here is the columns of A. If A, the matrix, has a pivot in each row, then the columns of A, a set of vectors, spans Rm. If A has a pivot in each row, then the equation AX equals B is consistent for all B in Rm. That's what it means for the columns of A to span Rm. That means the equation AX equals B is consistent for all B in Rm. We can also think of that as each B in Rm is a linear combination of the columns of A. When we're making linear combinations, we're making linear combinations of sets of vectors. And finally, if we see that A, the matrix, has a pivot in each row, then the linear transformation, T of X equals A times X, is what we call surjective. The other thing that we would, the other word that we have for surjective is onto. We would say that T maps Rn onto Rm. So surjective or onto. We need to be able to negate all these statements because we might observe that a matrix does not have a pivot in each row. Now we want to make sure that we negate our statements correctly. So let's suppose that we observe that A does not have a pivot in each row. We're going to make conclusions about the set of vectors, the columns of A, the equation AX equals B, and the transformation T of X equals A times X. And we want to make sure that these words go together with the right things. So if A, the matrix, does not have a pivot in each row, then we can say that the columns of A do not span Rm. Sometimes negating a statement is as easily as sticking does not in front of the verb, like we have in this case. If A, the matrix, does not have a pivot in each row, then the columns of A do not span Rm. The equation statement is a little bit tricky to negate. So if A, the matrix, does not have a pivot in each row, then the equation Ax equals B is not consistent for all B in Rm. So it'd be really helpful if we were allowed to use parentheses as grouping symbols when we're writing sentences. So we're saying that the equation Ax equals B is not, and then what follows is not consistent for all B in Rm. So we're reading it like this. It's not this thing. It's not consistent for all B in Rm. It's important to point these things out because you don't want to just say the equation Ax equals B is not consistent. That is not negating the previous statement. The previous statement said that the equation Ax equals B is this, consistent for all B in Rm. All of that is what we're saying it is. We don't get to shorten it. We got to include everything. So if A, the matrix, does not have a pivot in each row, then the equation Ax equals B is not consistent for all B in Rm. Another way we can express this is to say, if A, the matrix, does not have a pivot in each row, then the equation Ax equals B is inconsistent for some B in Rm. So here, the parentheses would go right after is. We're saying is, and then this thing, is inconsistent for some B in Rm. Excuse me. So it's all the stuff that comes after the verb, and the not goes with is in number 2. Finally, we can say if A, the matrix, does not have a pivot in each row, then the linear transformation T of x equals A times x is not surjective. That's one of the easier ones. We just stick not right in front of the thing. Another important note about the equation Ax equals B. It is not possible for the equation Ax equals B to be inconsistent for all B in Rm. So that's why we can't just replace not consistent with inconsistent, because we weren't just saying not consistent. We were saying not consistent for all B in Rm. We weren't just saying not consistent. We're saying not consistent for all B in Rm. This is an important distinction because the equation Ax equals B cannot be inconsistent for all B in Rm. This is because the homogeneous equation Ax equals 0 is always consistent. We always at least get the trivial solution. We always get the trivial solution. X equals 0 is the trivial solution. So this is why when you tried to negate this statement on one of your quizzes and said the matrix equation is inconsistent for all B in Rm, I said that's not possible. What you were trying to say is that the equation Ax equals B is not consistent for all B in Rm, or the equation Ax equals B is inconsistent for some B in Rm. Don't forget, the homogeneous equation is always consistent. We always have at least the trivial solution. So these are all the row things where we talk about the matrix, the columns of A as a set of vectors, the matrix equation, and the linear transformation. Those 4 things all connected together. The reason that I connect these 4 things through the pivots is that that is the observable thing. Usually we'll be asked a question, do the columns of A span Rm? Then we need to find an observable thing, and that's going to be the pivots. The question could come up, is the linear transformation surjective? We need to base our conclusion on an observable thing, and that will be the pivots. We'll say the standard matrix of the transformation has a pivot in each row, therefore the transformation is surjective. I also lay it out this way to make sure that we line things up correctly. The columns of A do the spanning. The equation is what is inconsistent or consistent, and the transformation is what is surjective or not. We wouldn't want to say that A is surjective. You're getting your point across, but you're saying it in a very strange way. You're playing tennis with a baseball bat. You are piloting your car. Your reader, depending on their level of experience with linear algebra, will know what you were trying to say, but you're still not saying it correctly. This is why I am so picky about your responses on the quizzes. So make sure you have the right words going with the right things. Don't say the matrix is consistent. That doesn't make any sense. It's an equation that is consistent. So these are 4 things that are connected to a matrix having a pivot in each row. That's the observable thing, a matrix with a pivot in each row. So this is called row stuff and column stuff. So let's look at some column stuff. If the matrix A has a pivot in every column, we're going to make conclusions about the columns of A as a set of vectors, the matrix equation AX equals B, and the linear transformation X to AX. So let's look at what we got. If A, the matrix, has a pivot in every column, then the columns of A are linearly independent. If A, the matrix, has a pivot in every column, then if the equation AX equals B is consistent, then the solution is unique. Notice that we can't say that the equation has unique solutions. Because the equation, if we have a pivot in every column, that does not guarantee that there will be a pivot in every row, so we're not guaranteed that there will be a solution. But if there is a solution, then the solution will be unique. So now we get down to how we usually define linear independence. If A, the matrix, has a pivot in each column, then the homogeneous equation AX equals 0 has only the trivial solution. This is why we can't just cite the trivial solution or free variables in absence of all the other stuff that goes with it. If A has a pivot in every column, then the columns of A are linearly independent. And we can also find that out by saying that the homogeneous equation AX equals 0 has only the trivial solution. Some of you wrote on your responses, the equation has only the trivial solution, and I said, what equation? It's the homogeneous equation that has only the trivial solution when the columns of the matrix are linearly independent. And finally, the linear transformation that takes X and maps it to AX is injective. Injective is another word for one-to-one. So once again, we want to make sure that we can negate each of these statements if we see that the matrix does not have a pivot in every column. So let's do that. If A, the matrix, does not have a pivot in every column, then the columns of A are linearly dependent. You could say not linearly independent, but that's a little bit clunky. We should say linearly dependent rather than not linearly independent. This gets a little tricky, especially when I do the awful thing of asking a yes or no question, and you want, when the answer is no, to use the word not in there somewhere. So let's just be careful about that. I'm not going to take off points if you're like all not linearly independent, but it's going to sound weird if you read it back to yourself. So if A, the matrix, does not have a pivot in every column, then the columns of A are linearly dependent. If A, the matrix, does not have a pivot in every column, then if the equation AX equals B is consistent, then there are infinitely many solutions. Once again, we are not guaranteed the existence of solutions, but if there are solutions, there will be many solutions. If A does not have a pivot in every column, then the homogeneous equation AX equals 0 has a non-trivial solution. These last two, we might want to use the phrase free variables. We want to say there are free variables. In which case I will say, what free variable? What has the free variables? Specifically, it's the equation or the solution set to the equation that has the free variables. If you say A has free variables, I will say A is a matrix and doesn't have variables at all. But if you say the equation AX equals 0 has free variables, that's what that means. However, if you observe that A does not have a pivot in every column, and just tell me that the columns of A are linearly dependent because the homogeneous equation has a non-trivial solution, I will say, how do you know? So at that point, you either need to demonstrate one of the non-trivial solutions, show that a linear combination of the columns of A is equal to a non-trivial linear combination of the columns of A is equal to the 0 vector, or just observe that A does not have a pivot in every column. Once again, pivots are going to be the observable thing. That's going to be the easiest thing that we can observe and then base our conclusions on. Finally, the linear transformation that maps Rn to Rm given by T of x equals A times x is not injective. That one's easy to negate. We just put not in front of the thing. Notice that when we're talking about pivots in columns, span doesn't come up. We don't have anything about existence of solutions, span. We're talking about independence and uniqueness and injective. When we were talking about rows, we weren't talking about independence, we weren't talking about uniqueness, we weren't talking about injective. We were talking about span, existence of solutions, consistent equations, and surjective. Those are the things that go with rows. That's the row stuff. This page is the column stuff. So that's why I separate this out into row stuff and column stuff. What do we know when we observe the pivots in the rows? What do we know when we observe the pivots in the columns? All right, I'm going to pause the video here, and we will, when we come back, we will start talking about linear transformations. The short story is that when we have a linear transformation, we can always write a matrix, find a matrix that implements our linear transformation. So we got to learn what a linear transformation is and how matrices are involved in linear transformations. I suppose there should be some stuff about why linear transformations and why we care about linear transformations. But we're going to start with what a linear transformation is and what matrices have to do with linear transformations. All right, I'm going to pause the video here, and we'll come back and talk about linear transformations.